Today we're going to begin chapter 21, and with that we're going to continue on in our discussion of carbonyl chemistry, which is super important since it occurs everywhere, including in biological systems, and also the chemistry of carbonyl groups is used all the time in industry, making materials, making pharmaceuticals, and on and on and on. We already know how we can do nucleophilic acyl addition reactions to aldehydes and ketones. But what if rather than an aldehyde or ketone, one of the two groups in our carbonyl carbon is something that can act as a leaving group? Then we have the possibility for nucleophilic acyl substitution reactions of this type. And that's the subject of this chapter. And I'm being here really general, being really sloppy with charges, let's say, but this is in general the type of reaction we're talking about. And it's going to depend, as you can imagine, quite a bit on what that group Y is, which we're going to get to. And so, do you mind? Can you just not? Now, I'm going to make her teach the class. Okay. Has to be the center of attention. Anyways, so where were we with that? I think that's about all I need to say about that. But this is the type of reaction that we're going to cover in chapter 21. So as you can imagine, you probably already guessed I would say this. The mechanism of a nucleophilic acyl substitution is neither SN1 nor SN2. It's really its own thing. So we'll start to cover that today. We'll do already one or two good examples of nucleophilic acyl substitution. We've already covered the nature of the carbonyl group in general. Everything we've said still applies to acyl derivatives of this type. Of course, the major contributor to the structure of the molecule is this one here with no charges on any atoms. This structure does play a role, though. And of course, depending on what Y is, that group is also going to affect the reactivity of this carbonyl carbon. I think Barnaby is chasing something. I don't know what he imagines he's found. Anyway, probably a bug. I hope it's a small one. Anyway, so of course, if this atom Y over here has additional lone pairs of electrons, then they can donate them to the carbon, and you have a situation much like we've already discussed in chapter 20 with carboxylic acids, where we learned that carboxylic acids are much less reactive than other acyl derivatives. And in fact, what we're about to find pretty soon is that carboxylic acids are the least reactive of all the possible acyl derivatives because of the effect of donating those electron pairs on the oxygen due to resonance. There's also inductive effect arguments, as you can imagine, as there always are. If this group Y is very electron withdrawing, for instance, by the inductive effect, well, that's only going to make this carbonyl carbon all that much more reactive towards nucleophilic acyl addition or substitution. So all of those things still hold true, and we'll unpack how that all works during this lecture today. So by the way, please do register your attendance. I'm not doing reef polling today. You just had an exam. I figured I'd go easy on us all today. Good. So let's get a little bit closer into the nature of these acyl derivatives and the effect of structure on reactivity. One thing that I think is going to be a surprise to no one is the more hindered that carbonyl carbon is, well, the less reactive it will be. And so what I've done here is, again, going by that phrase that I like so much, other things being equal, here other things are equal. I'm looking only at acid chlorides. as my carbonyl-containing compound. So any variation there is taken off the table. But I don't think anyone here would be surprised that if we go from a tert-butyl group to a slightly less bulky isopropyl group to a slightly less bulky still ethyl group to a methyl group, well, then we're going to get more and more reactive as that series continues. Or you could say that as we get less and less steric bulk, other things being equal, so keeping the same acyl derivative, assuming also the same nucleophile, by the way. But as we go down that series, the reaction will get faster and faster as the acyl derivative becomes less bulky. Again, I don't think that's going to come as a surprise to anyone, but bears mentioning anyways. What about the nature of the acyl derivative itself? Well, we do have an order of reactivity of acyl derivatives, which is as you see here, and that's really important. That's going to be something that you'll need to know as we go forward. When I say no, I don't mean know at page it's on so you can look it up. You'll have to internalize it, at least to some degree. And what you see here in this order of reactivity is the combined effects of resonance, you know, with your lone pairs on adjacent atoms, you know, that's able to stabilize that carbon, and the inductive effect. So electronegativity and the inductive effect also plays into it. But when all is said and done, I think you'll find that other things being equal, so again, assuming we're treating with the same nucleophile, assuming that these R groups are at least somewhat close to being the same, you know, it's not fair making one really huge and one really small, but assuming all of that, assuming all other things are equal, then I think you'll find that carboxylic acids are the least reactive acyl derivative, followed by amides, followed by esters. And thioesters are a strange one. Your book mentions these only because we're going to run into thioesters in later chapters on metabolism, so especially chapter 29. Thioesters show up a lot in biological systems, and so it's good to remember, I think, that thioesters are kind of like esters but more reactive due to the bigger sulfur atom here. Still more reactive than thioesters are acid anhydrides, and most reactive of all are acid chlorides. And candidly, anhydrides and acid chlorides are pretty close to the same reactivity, but I do have to give the slight edge to acid chlorides. I think in general, they're just a little bit more reactive than acid chlorides. And you could, if you wish, say acid halides here, but I think in practice, you're going to find 99+% of the time, if you've got an acyl halide, it's going to be an acid chloride. Acid bromides do exist. They can be made. Actually, we're going to learn how that's done today. But for what it's worth, I've never made an acid bromide, nor have I ever had any reason to. Either way, whether you make an acid chloride or an acid bromide, it's nice to bear in mind that they're made from carboxylic acids, and that's a very good thing because it means that with just one reaction, we'll learn these reactions today, you can go from the least reactive acyl derivative to the most reactive acyl derivative. So that's a very important type of reaction to be able to do. And we'll cover that today as well. But I think in practice, you'll find it's going to be acyl chlorides or acid chlorides that wind up getting used here. They're the ones that are, there's the most of them available commercially. I just have never really seen an acid bromide used in preference. To the extent that I've looked at the literature, I just have not seen that happen. I think there even might be one or two acid fluorides that are known. I'm pretty sure that you can buy acetyl fluoride. I can only imagine how nasty that stuff must be. It probably eats glass. And I think it's also a gas at room temperature. So I wouldn't want anything to do with it myself. But anyway, this is the order of reactivity of the acyl derivatives. And what that means for us, we'll get into this, I think, more so starting on Monday. But one thing this means for us is, in general, it's going to be easier to go from a more reactive derivative to a less reactive derivative. The only exception being that we have a way to go from a carboxylic acid directly to an acid chloride. But we're going to find, for instance, that you can aminolyze an ester. This is probably Wednesday's material. You can aminolyze an ester and go to an amide, but you can't alcoholize an amide to make an ester. If you treat an amide with an alcohol, no reaction. They just look at each other. So that's yet to come. We'll get to that next week. One thing that I think you will notice if you keep your eyes open and are fair-minded about it is, again, roughly speaking, this is not an exact type of thing, but I think if you look at the different groups that are attached to the carbonyl carbon, the ones we called Y up here, I think if you look at the order that they go in, you'll see that more or less, it's not exactly perfect, but more or less, the order of reactivity of the acyl derivative towards nucleophilic acyl substitution is roughly the opposite of the order of reactivity towards electrophilic aromatic substitution when you put those same groups on a benzene ring. And the reason why I think is important for you guys to know, because it will help you understand this material better. And so that's why I even said here in your class notes, don't just memorize that sentence. Understanding the reason, I think, is going to be very helpful. It's not complicated. I think you can handle it. The reason, so we're talking about, again, the nature of this group Y and the effect of the group on a nucleophilic acyl substitution, which will look something like this once we start getting into the mechanisms. Again, give or take whether we're an acidic solution and have to protonate the oxygen first, give or take the nature of the nucleophile, whether it's neutral or anionic. So leaving all those details aside, something like this is going to happen in a nucleophilic acyl substitution. It would also happen in a nucleophilic acyl addition reaction. And so in any case, you've got your organic substrate here, your carbonyl compound, reacting with a nucleophile, and a nucleophile needs to attack it. And so what is the question is, what is the effect of this group Y on how easily or how easy or difficult that step is? Meanwhile, if we consider that same group Y attached to a benzene ring, and we look at electrophilic aromatic substitution reactions, well, here we're expecting the organic substrate to do exactly the opposite thing. Here, our organic substrate is not reacting with a nucleophile, it's reacting with an electrophile. The nucleophile is the aromatic ring. So no wonder the effect of Y is going to be roughly backwards to the effect on reactivity towards electrophilic aromatic substitution. Here we're expecting the benzene ring to give up an electron pair as compared to the reactivity of that same group Y on an acyl derivative in a nucleophilic acyl substitution. Here, the carbonyl carbon is going to accept an electron pair from a nucleophile. Over here, we have our organic species giving up an electron pair towards an electrophile. So no wonder those two things are, roughly speaking, opposite to one another. I think it makes a lot of sense. And I think understanding that is going to add to your understanding the reaction. Even the very names of the reactions give the game away, right? Nucleophilic acyl substitution, electrophilic aromatic substitution. No wonder they're kind of backwards from each other. So it's kind of a subtle point, but I think it's a worthwhile point to bring up. So I did. Good. So I think that gets us through here. Good. And so for the list is backwards for benzene rings, like, well, not acid chlorides, but halobenzenes. So if the Y is a halogen, and then instead of a carboxylic acid, instead of putting the OH in a carbonyl, we're putting the OH in an aromatic ring. And I think you'll see that's true, right? The OH is much more activating than the chlorine on a benzene ring, if that makes sense. So it's not that you have an acid chloride here. It's all about this group Y on a benzene ring, or that same group Y on an acyl derivative. And the way to know what Y is to look at what is the group that's attached to the carbonyl. Here it's OH, here it's an amino nitrogen, alkoxy over here, alkyl thio over here. Here you've got kind of an acyl oxy group, an ester group, and here Y is your halogen. So that's how you know what Y is. Make sense? Any other questions on this? I was telling my first class, I try my best to remember when I ask if there are questions to actually wait for questions. I don't always remember, but I try my best because I actually had one professor I had as an undergraduate. We called him Fast Eddie. He literally was the type with chalk in one hand and eraser in the other. And it was kind of scary. So, and I had this other professor in grad school who was the type to say, any questions? Now we're going to talk about it. So you do very fast. They were both good teachers, actually, but it was just a little scary getting used to them. Good. All right, so it seems everyone's pretty comfortable with this sort of reactivity. That's going to matter, probably more so next week, Monday and Wednesday. But we're going to see that come into play, I believe. Good. Well, let me just get that window ready. Are there any things you can't have as a Y group? What else might you like that's not included here? I mean, certainly all of the smaller main group elements. We've mentioned the halogens. Certainly, I don't think you're going to find too much other than this. I don't think there's anything obvious that's missing. You've got oxygen, you've got nitrogen, you've got halogens. Once your Y group is a carbon, by the way, then you no longer have an acyl derivative. Then you have a ketone. If it's hydrogen, you have an aldehyde. So those things we covered. In that sense, it's reasonable to point out that in chapter 19, we had nucleophilic acyl addition reactions of aldehydes and ketones. Can you put a cyano group there? Those do exist. They're called Acyl Cyanides, but I don't think you'll find they're really that much different from acid chlorides, and a good deal more dangerous. Just to clarify, only when the aromatic rings Y is a halogen, the reactivity is reverse. No, I think the reactivity is reverse all the way through, more or less. Imagine if Y is an OH, that corresponds to the carboxylic acid, right? And so with OH in an aromatic ring, I think that's the most reactive of the bunch. Whereas it's the least reactive with the acyl derivatives. And certainly with a halogen, I think that's the least reactive of the bunch when it's on an aromatic ring, right? Because halogens are ortho-para-directing, but deactivating, because they're so, they're so, hey, when I can't think of a word. Well, they're so good at sucking electron density, right? Because, yeah, that's okay. They're so electronegative, that's the word I wanted, right? So they're sucking electrons out. Meanwhile, if we're sucking electrons out of the carbonyl group, that's going to make the carbon more reactive towards a nucleophile, but it makes the aromatic ring less reactive towards an electrophile. So no, these are good questions. It's kind of a subtle point, but I think it's an important one. So I'm trying to remember. Oh, I was saying about acyl cyanides. I've heard of them. I don't think they're real stable. I don't think they would behave all that much different from an acid chloride, with the added bonus that you're in danger of generating HCN gas and people dying. So, you know, I've never heard of them really being used. At least I'm not aware of a reaction in which those are used. Good. So with that being said, let's then continue on with some reactions of nucleophilic acyl substitution reactions that involve carboxylic acids and also other reactions of carboxylic acids. So a lot of this is review. I think we've already talked about thionyl chloride as a reagent to convert carboxylic acids to acid chlorides. And again, this is very useful because you're going from the least reactive acyl derivative to the most reactive one in one reaction vessel. So I just thought I'd point out phosphorus tribromide is the reagent of choice if for some reason you wanted to make an acid bromide. I would not say you're responsible for that mechanism, but not that it's all that hard. I mean, you can probably guess what the first step is. We already said that oxygen loves phosphorus. What about, you know, the oxygen glomming onto the phosphorus? I'm sure that's the first step. What about then maybe a bromine adding into the carbonyl carbon? And one way or another, the phosphorus atom is going to get rid of this OH group and replace it with bromine. So it's not a complicated mechanism. I just don't think we really need to worry about it for a relatively unimportant reaction. But phosphorus tribromide is the reagent of choice. What about a solvent? If I were using a solvent, I sure wouldn't want to use anything too much more polar than diethyl ether. Certainly you would need an aprotic solvent because PBr3 will react violently with anything protic. I'm kind of worried about this OH group and that thing. You're going to get HBr and it's going to be nasty. So in fact, I like I said, I've never done this. I wonder if you might just do the reaction neat with no solvent. Just add your carboxylic acid into the phosphorus tribromide. And you could then isolate the acid bromide from that if you're careful, because I expect that'll be really reactive. So I would expect if there is a solvent, it's going to be something really unreactive, nothing more polar than diethyl ether. I wonder if you could even use an alkane or maybe dichloromethane, or maybe no solvent at all. But anyway, if for some reason you needed to convert the carboxylic acid to an acid bromide, phosphorus tribromide is the reagent of choice. We much more often are interested in converting a carboxylic acid to an acid chloride. I think the mechanism in your book is fine. And I'm working through it here using benzoic acid as an example. And so here's thionyl chloride, it's SOCl2. So it's important to know that structure, I would say. The only nitpick we might have with this mechanism is using a halide ion as a base. And remember what we've said about that. You're only going to use a halide ion as a base when there literally is nothing else. And my understanding with the thionyl chloride reaction, the closely related oxalyl chloride reaction, my understanding is that usually we like to add a mild base, an amine base, to go along with this, to help mop up this HCl. So that could be pyridine or triethylamine. You could even use that as your solvent. And in those cases, so look to see what you're given, right? If you're not given any amine base, then I guess that mechanism's fine. But if you're given pyridine or triethylamine or some amine base like that, then that's what you'll want to use to pull that proton off. Because I mean, those are not the strongest bases in the world, but they're way stronger than a halide ion. So, and I'm pretty sure I have done this type of reaction. I thought that you had an amine base along for the ride. Be that as it may, the mechanism I think is otherwise not that mysterious. This first step of the carboxylic acid adding to thionyl chloride, I think it's okay to think of this as kind of like an SN2 reaction. I know it doesn't look like it because of the sulfur-oxygen double bond, but then again, I would expect that sulfur atom to be sp3 hybridized, not sp2, because of that extra electron pair. So I mean, it might be that sometimes it breaks the sulfur-oxygen pi bond, then that bond reforms and kicks out a chloride. Maybe. I wouldn't be shocked if both those things happen, but I think this step is fine, drawn that way. In the next step, we want to go to a neutral derivative so that we can keep going. So whatever base we have on hand, chloride if there is no other base on hand, but look and see if you're given some amine base, in which case you would use that as your base here to pick off the proton. After that, chloride can act as a nucleophile onto the carbonyl carbon. Chloride isn't a particularly great nucleophile, but the thing is, after this next step, in which this whole thing collapses, and you see that you generate a molecule of SO2, which is a gas, and another chloride ion, I believe we're dead even in chloride ions. Here, I'm giving you a chloride ion. Here, I'm taking it back. Here, I'm borrowing the chloride ion from you, and here I'm giving it back to you. So I think we're dead even on chlorides. So there's no chloride being either generated or consumed here. This step is the one that provides the main driving force, because you're making this gaseous inorganic byproduct, SO2, that will bubble out of solution and now is gone. So that's going to drive the reaction forward. I'm sure you're all noticing also that in this mechanism, we have both plus and minus charges. The way that you know you can do that is when you look at what you're given and you don't see any particularly strong acids or bases. So that's an indication that you're at or near pH 7. And that's why it's okay to draw the mechanism like that. I don't think we'll run into more than a small handful of these that are run at or near pH 7. Mostly when we do reaction mechanisms, I think you'll find they will be decidedly an acidic solution or decidedly an alkaline solution. So this is not common, but maybe a few more times, maybe 2-3 more times, we'll run into reactions that are like this, that are neither particularly acidic nor particularly alkaline. And you can know based on what you're given. If you don't see anything that's particularly strongly acidic or alkaline, then you can assume that you're right around pH 7. And so we're okay with both pluses and minuses. Really, the actual rule of thumb that we mostly use is there a solvent for this reaction? Well, yes, if you're using an amine base, like pyridine or triethylamine, then that'll be your solvent. Otherwise, I don't know that there necessarily is a solvent. So, but you'll know what it is based on what you're given. What else was I going to say about this? Generally, if you want to know the in many ways subtlest but the most complete way to think about how you can know whether you can have this or that species in your mechanism, we have a rough Pka rule. I'm putting it in chat. You don't want to have a Pka difference more than about 7 or 8. So I put it in chat. Somewhere round and about there is the most you want to go. But you want to be sure in any case that you're not bringing two species together in the same reaction mechanism that are further apart than about 7 or 8 in pKa units. More than that is really hard to justify. But up till then, you're probably fine. So for instance, let me see here. We've got our carboxylic acid. So what's that pKa? What do you want to say, 4 or 5, something like this? This one probably is a pretty low pKa. I'd anticipate 0 or 1 or maybe -1, but we're still within 7 pKa units. What about that guy over here? Well, it's the I don't know how we would consider that as, because you're not even going to get the conjugate acid. You're not even going to have a chance, because as soon as you form that guy, it collapses. So all told, I think we're pretty much fine in terms of pKa values. So the reason I bring this up is you'll remember how I've said in acidic solution, we don't want any strongly basic anions, which is true. And in alkaline solution, we don't want any cations. Anything other than metal cations anyway. So no carbocations, no oxygen with a plus charge. Those species don't make sense in alkaline solution. They couldn't exist. They would immediately either suffer nucleophilic attack or be deprotonated. to get rid of that plus charge. And that's just another way of stating this Pka rule, I would say. So if you want a nice, simple to state, maybe not quite as simple to apply, but certainly simple to state in a few words, if you want a rule that's like that, I would say that's the way to think about it. The other things we've said, you know, no strongly basic anions in acidic solution, no cations, except for metal cations in alkaline solution. This is just another way of stating the same thing, really. But you can think about it either way. Good. So I think that's all I need to say about that. Something you might see used instead of thionyl chloride, SOCl2, is oxalyl chloride. And I've seen both names, oxaloyl chloride or oxalyl chloride without the second O. Both are fine. You can use either name. I've heard both used. Oxalyl chloride is actually the diacid chloride of oxalic acid, which I think is something you might have heard of. So replace both chlorines with OH and you've got oxalic acid. Oxalic acid is the smallest of the dicarboxylic acids. It is just 2 carbons. There's a silly mnemonic device for the dicarboxylic acids. And of course, I remember the mnemonic device, but not so much how to use it. But it was, oh my, such good apple pie, sweet as sugar. So O for oxalic acid, M must be for malonic acid, oh my, such, S for maybe succinic acid, good, what's the G for? Oh, was it glutaric acid? No. I remember the stupid mnemonic device, but it does me no good. Anyway, oxalic acid is the smallest of the dicarboxylic acids. And you might have heard of oxalic acid. Oxalic acid is the bad actor and the reason why we can't eat rhubarb leaves. Rhubarb leaves are highly toxic because they have a lot of oxalic acid, not oxalyl chloride, but oxalic acid in them. And so that's why you can only eat rhubarb stalks, but not rhubarb leaves. So if someone in your family is making the strawberry rhubarb pie, I highly recommend it. I'm fond of it. You might not like it, but that's totally fine. Rhubarb stalks are fine. Rhubarb leaves are no good. They have too much oxalic acid. That then gets into your kidneys and combines with other ions like calcium. You get calcium oxalate, and that's otherwise known as kidney stones. So that's a problem. But rhubarb stalks are fine. They don't have the oxalic acid in them. Anyway, what I'm saying here is oxalyl chloride undergoes the very same type of reaction. And that might be a challenge that I'll leave to you guys. See if you can work out the mechanism with oxalyl chloride. Just replace the thionyl chloride with oxalyl chloride. I think you'll find it's very, very similar, except it's even a little bit more exciting. This step at the end is sort of, you've got the whole thing falling apart like crazy. And you should find that at the end, your gaseous byproducts besides HCl, rather than getting SO2 in HCl, you'll get carbon monoxide, carbon dioxide, and HCl. So give it a try. I think that will be worth your trouble. And as always, if you work that out and not sure if you did it right and you want to show me your work, don't hesitate. That's what I'm here for. Good. So both of those reagents, both oxalyl chloride and thionyl chloride, can be used to convert a carboxylic acid to the corresponding acid chloride. What are some other reactions of carboxylic acids? Well, one of them is esterification. And there's at least 2 good ways to convert a carboxylic acid into an ester. One, which is actually used much less often, you could call it esterification by an SN2 reaction. And one would start with a carboxylic acid that you would then deprotonate. You would treat it with some base. And sure, you could use sodium or potassium hydroxide in water. That's fine. But you don't even need to go that far. You can use a much milder base like sodium bicarbonate. So that's your baking soda, right? Or sodium carbonate if you like, Na2CO3, fine. Would also work. Either of the above will deprotonate the carboxylic acid. You'll make carbonic acid, H2CO3, which is pretty unstable, and will break up into water and CO2 gas, and you'll see the CO2 gas bubbling out. Of course, H2CO3 is what is in your carbonated beverages. I call it soda. I was in the Midwest for a long time, and they all called it pop. I think down, at least in certain parts of the South, it's all just Coke, regardless of whether it's orange soda or Sprite. Whatever you wish to call the carbonated beverage, the bubbles in that carbonated beverages are, of course, carbon dioxide coming from carbonic acid. Here we generate carbonic acid, so we deprotonate the carboxylic acid, making the carboxylate ion. So that now is going to be a nucleophile. And it may not be the greatest nucleophile in the whole world, but with a big fat primary alkyl halide of this type, especially if it's primary, it's good enough. And this will then undergo an SN2 reaction. Doesn't even really matter so much what the solvent is. You can use a protic solvent. It'll just be slower, but it'll still work. And you would wind up getting an ester of this type. Strangely, that method is not used so very often. I don't really know why. I've never done a reaction like that, but I would look forward to doing so. I would imagine it would be very successful. Very mild conditions, you know, as long as you don't wind up taking a bath in the primary alkyl halide, you're fine. So I don't know why. Much more often used is Fischer esterification, which we introduced way back last term in chapter 17. Fischer esterification is one of those reactions where at least 3 or 4 times over the course of your life in organic chemistry class, at least 3 or 4 times you've heard me say, or you've heard your other instructors say, so here's Fischer esterification, you're not responsible for the mechanism yet. Well, guess what? Yet is now. Now we finally get to learn that mechanism because it's a nucleophilic acyl substitution reaction. And so very similar to other reaction mechanisms that we'll get to Monday, Wednesday of next week. So, right, so, but I'll just remind you what the overall reaction looks like. We take the carboxylic acid, it's very general, R1 can be most anything. We essentially dissolve it up in some alcohol, and I'll let you know, probably 97 to 98% of the time, R2 is either methyl or ethyl, so you're using either methanol or ethanol. And then we add a little bit of an acid catalyst, maybe a few drops of sulfuric acid or something similar. And we heat that up generally to reflux. That's really convenient because both methanol and ethanol have reasonably well-behaved boiling points. You know, they're not that high. Methanol, I think, is around 60, ethanol maybe 80 to 90, somewhere in that range. And so you let that reflux for a while. And over the course of the experiment, you will liberate 1 molecule of water for every molecule of the ester you make. That water is not going to have any effect whatsoever on the reaction, since, as we'll see in a moment, the water molecules are very greatly outnumbered by the alcohol molecules, so they're pretty much a non-factor. But other than that, it's pretty general for R1 and R2. As long as R1 and R2 don't have any other functional groups on them that are sensitive to strong acid, as long as they can stand up to the acid, you're fine. It's otherwise very general. I am not happy this time with the reaction in the book. And so some of you have asked about that, and it's a reasonable thing. I would say in general, if you see me go against something that's in the book or something that's in OWL, and you're wondering which way to learn it, in general, do it the way we did it in class. Do it the way I cover it in class or in the class notes. Not because I think I'm something great and fantastic, but because when I do that, I generally have good reason. And I do believe that the mechanism in your book has problems, as mechanisms often do. Not always, but often in your book. Often they like to conflate 2 steps, you know, smush 2 steps together that really are separate steps. And I believe I have a pretty good handle on that experimentally. Like they like to combine multiple proton transfers. That's not going to happen in the absence of an enzyme. Yeah, that's the main problem, is they like smushing multiple steps into one. And I don't like that. I don't think it comports to reality. So the first step is going to be, just as we saw in chapter 19, protonating our carbonyl oxygen with whatever is available to be the acid. And again, when I look at what I'm given here, all I have is ethanol and the little bit of acid that I added, which of course will immediately dissociate. If it's sulfuric acid, you'll get the bisulfate ion, HSO4-, and it'll put protons on some of the alcohol molecules. Not all of them, of course, but on some of them. And that will be instantaneous and quantitative. So we'll use the conjugate acid of our solvent, not H3O+, right? We don't have water present. It's not mentioned here. So we can't use it, or use water or H3O+ in our mechanism. So we use this conjugate acid of our solvent to put the proton on, and then just like before, our nucleophile attacks. So that will be our ethanol. Again, not ethoxide ion. It doesn't make sense to have ethoxide ion present in an acidic solution. It's too strongly alkaline. You know that because the pKa of ethanol is like 18 or 19. And if you can, here's that Pka rule again. If ethanol is a pK of 18 or 19, and we're at maybe pH 1, 2, 3, something way down there with the addition of a strong acid, we're way too far away to be able to have any concentration of ETO- at all. So that's an example of using that Pka rule. But once we've had that addition, just like before, I think you're already used to this, we got to do some proton transfers. And again, we do them one at a time. The reason for the proton transfers is to make sure that the right atoms have a plus charge and the wrong ones do not have a plus charge in order to make the reaction go forward. And again, these two proton transfers are not going to happen at the same time. That would not make sense. Remember that you covered this in Gen Chem when you talked about activation energies, where you know it's rare enough for two molecules to collide with the right speed and the right orientation to react. It's rare enough for two molecules to collide like that, let alone 3 or 4. That's just not going to happen in the absence of an enzyme. And again, the reason we can't just put that proton straight on that oxygen, well, you'd have a 4-member transition state, 1, 2, 3, 4. That's not going to happen either, not unless you're a Wittig reaction. But short of that, you're not going to have a 4-member transition state. So we first pull off this proton, and then we'll use again the conjugate acid of our solvent to put a proton on the OH group so we can lose that as a molecule of water. Now, how do you know which order to do those 2 steps in? Well, again, I think if you look carefully and you're fair-minded about it, you'll see it makes the most sense to do it in this order. If we did it in the other order, if we protonated this oxygen first, well, then you'd get an intermediate with a +2 charge. And I think you'll agree that doesn't make a whole lot of sense. Better to go from +1 to 0 charge and then back up to +1 than to go from +1 to +2 and down to +1. So I think you'll agree this order makes the most sense. And if you just put a little bit of thought into it like that, it becomes so much easier to remember when you understand it. So that's the reason I bring it up. Anyway, we protonate this oxygen. Now we're able to lose our water molecule as a leaving group. Just as we've seen things like that happen before, this is the elimination part of the substitution. At that point, we basically have our product. We just need to pull off a proton, and we can use our solvent molecule for that. Again, ethanol as opposed to water, we do generate a water molecule, but this water molecule is now floating in this ocean of ethanol. Each water molecule is outnumbered by probably 10 to the 15th or 10 to the 20th power to 1. There's no way water or H3O+ are going to be factors in this mechanism. It's just too far outnumbered. So instead, we use a solvent molecule to pull the proton off, and we're done. So that's the mechanism of a typical Fischer esterification, the way I'd like you guys to learn it. I'm not entirely happy with how the book does it. Good. Questions on that mechanism then? You mean I did it again? I'm such a good teacher that no questions are possible? Yeah, I can believe that if I want to. Anyways, one other thing I wanted to mention, a common question at this point is, why can you not do this reaction under alkaline conditions? And this is already in your class notes, but I thought I'd just point it out. Well, let's think about that for a moment. Let's say we dissolved our carboxylic acid, whatever it might be, in our alcohol, whatever it might be, And instead of adding a bit of acid, we added some sodium or potassium hydroxide. Well, all that's going to do is immediately deprotonate some of these carboxylic acid molecules, and now the reaction's dead. No further reaction can happen. How are you going to get another nucleophilic addition onto that carbonyl group to make O- when the particle already has a minus charge? So that's a way that you might use to remember that we can't do Fischer esterification under alkaline conditions, only acidic conditions. And that will vary. Some acyl reactions can occur only under alkaline conditions, some only under acidic conditions, some under both. And that will just depend on the nature of these groups. But we'll get to examples of all of them. And I think at the time we'll be able to make some sense as to why it occurs that way. So I have 1 minute left. So I just want to point out another reaction of carboxylic acids, that's what this section is on, is one we know already. You can reduce carboxylic acids to primary alcohols using LAH or borane, BH3. Borane is an excellent reducing agent, and you can swap lithium aluminum hydride out for that. Boron would love to get rid of those weak boron hydrogen bonds and replace them with strong boron oxygen bonds. So that will also work. Another reaction that we're going to mention here, but we're not really going to unpack until chapter 26, which I think is coming up next, actually. That's the chapter on peptides and proteins. But it is possible to convert a carboxylic acid to an amide using either a primary or a secondary amine. So you need at least one NH bond here. And a material called DCC, which stands for Dicyclohexylurea. And I just thought I'd show you what those two compounds look like. So, dicyclohexyl carbodiamide is the species you'd use to convert the carboxylic acid to an amide. So DCC is dicyclohexyl carbodiamide. Interesting structure. That central carbon is, of course, sp hybridized, just like in CO2. Also, please take note, those really are cyclohexyl groups, not benzene rings. Why? Couldn't tell you. For some reason, they use the reagent with cyclohexyl groups. And this reagent is also used to make peptide bonds, because isn't a peptide bond nothing other than an amide functional group? So that's why we'll bring this up again in chapter 26. We use that very same reaction to make polypeptides in the lab. The byproduct is dicyclohexylurea. Urea is just H2N C double bond O NH2. It's kind of like double amide. Again, I don't really love making you guys memorize structures, but if you had to memorize a few structures, urea is not a bad one to learn. It's a small molecule and it pops up a lot. So NH2 C double bond O NH2, and we just replace the two hydrogens with cyclohexyls. That's going to be your byproduct of this reaction. And I think you can see what's happened. If you compare the formula of dicyclohexyl carbodiamide to dicyclohexylurea, I think you'll see the difference is H2O. And that's exactly what we've done. We've removed water from the system in the form of the hydrogen on the primary or secondary amine and the oxygen that used to be in the OH group. So HOH, there you go. So you're not responsible for this mechanism yet. We'll go over it in chapter 26 when it will be a little bit more relevant than that.